your class and a weekend to let you kind of prep for that, because the last thing I'd want, especially if you struggled on exam 2, is to hammer you right away with exam 3, because there's not going to be enough time to get ready for that exam. It's going to be covering all the content that we covered up through that point. That includes everything that was on exam 2, so you're going to have that handy as well on those common information sheets when you use them. So when I hand back exam 2, I'll say a little bit more about what happens on exam 3 in the final, and then we'll just sort of get through the content as we can. The redemption points that I mentioned over the break, they're up front. They're these worksheets that contain really the most core elements of what happened on exam 2 to make sure that you understand what was important, and if you still have a hole, to come talk to me or go get extra help about what's on that assignment. And these are due on 4/10 before I get to work. That just means you can slide them under my door at 6 a.m. on 4/10. As long as I'm not there, I'll take it. So you have a long time to do it. Do them, get the points. And of course, those points go into your course grade. Those are the best points, right? So it doesn't matter. It doesn't matter if I'm going to drop something or whatever it is. These points are yours, and they go into your overall to help all the things that you want to miss points on. So, okay. So any questions with that? All right, let's keep going. And let's put that up on the board. So let's go to there and go here. What I didn't get to. So exam 2 for you guys was a little bit truncated for what should have been on there, just because I'll admit, these wonderful discussions that we have, I want you to keep asking me questions. I can't just be a runaway freight train. So ask me questions, I will answer them, because that's really the most important piece. This piece then ended up getting cut, but it certainly is going to be on exam 3 and the final. So this is chapter 9-8 to the very end. So the one thing I dropped off, and it's kind of it's not a throwaway reaction, but it's something that's very much related to when you use potassium permanganate with alkenes, the same types of oxidative cleavage chemistry happen with alkynes. So in other words, in this case, unlike in alkenes where ozone gives you back aldehydes and ketones, if you don't have substitution there, the potassium permanganate and ozone with alkynes end up leading to the cleavage of the carbon-carbon triple bond. And if there is a hydrogen on the carbon, which in this case there isn't, you end up getting back carboxylic acids. It gets oxidized all the way up to the carboxylic acid, just like alkenes get oxidized all the way to the carboxylic acid with potassium permanganate. If you have a terminal alkyne, meaning that you have some R group over here, alkyne, and an H on it, and you expose it to potassium permanganate or ozone, you end up getting back the carboxylic acid from this side. And if there's an H on that carbon, just like with alkenes, that side gets oxidized all the way up to carbon dioxide. So it's a cleavage reaction where if there's a hydrogen on that carbon, that side becomes CO2 and gets cleaved away, and the other side becomes a carboxylic acid. So this is very similar to what happens with the alkenes, except now ozone can complete that chemistry. So that's kind of the last little, those are 2 reactions that you have to have on your common information sheet or in your head. Now we run into something that is truly, truly important for this class, because it's the first freaking time we make carbon-carbon bonds. This is a class about carbon, and up until this point, we've just destroyed carbon-carbon bonds. This is the first time that we can snap those together, which makes it truly important reaction, at least for you guys. When you get to 314, there's a ton of other ways to do it. So this is the first one. So if you have an alkyne, the acidity of that terminal alkyne, that hydrogen, is so low that you can use relatively strong bases and deprotonate the alkyne to make what is called an acetylide anion. So what am I saying? So in this case here, you have an alkyne, and because of the nature of that bonding pattern with C triple bond C, this H is so acidic, and I'm not saying like sulfuric acid level, like 25, 20 pKa on it. So it's a very acidic value compared to, let's say, methane, which is 50. So in this case here, this hydrogen is so acidic that if I was to expose it to a pretty strong base, and of course the base has to be strong enough to remove that hydrogen, so we come in with sodium amide in some sort of solvent. It gets a little bit debatable on that one, on what you actually the perfect solvent to use. Mostly something that would dissolve that. That if you add this to this alkyne, what you end up getting back is the deprotonated acetylide anion. This acetylide anion can act as a base. It can also act as a nucleophile. So as we've had these reactions where something comes in and attack, for example, any reaction where we have, for example, if we use HBr plus this alkene, of course we know that we would, of course, protonate first, create a carbocation, and then something attacks. That attacking piece is bromide here. In this case here, acetylide ion can act the same way. So the first thing that I want to bring up is the fact that if you have an alkyne and you expose it to base, you can deprotonate alkynes to make acetylide anions, which create a very reactive species. And of course, as I just mentioned, if you look at the relative pKa's, meaning the strength of those carbon-hydrogen bonds, as you go from alkyne to alkene to alkane, the pKa goes up, meaning that those hydrogens, carbon and hydrogens, are becoming more and more difficult to remove. And for alkynes, it ends up being relatively easy compared to the other possible carbon-hydrogen bonds that we can use. So acetylene can be deprotonated by a conjugate base of any pKa greater than, well, it should be 25%. It should be greater than 25. There's no value on it. Right? I have to have something that has a pKa that's lower than that to drive that reaction to completion. So why is this happening? Well, it has to deal with acidity is based on the percentage S character in the bond that is accepting those electrons. Okay, so what does that mean? It means that when I describe the hybridization of this carbon right here, we would all say it's sp hybridized. So if I was to describe how much S character is in that orbital, that hybrid molecular orbital, it would be 50% S and 50% P. And so my question to you is, why does the S orbital generate stability? So this would be the general feeling, this would be the general characteristics of an S orbital. And of course there would be a nucleus in the middle here. So why does more S character of that orbital stabilize an anion or negative charge? What are we comparing it to? We're comparing it to a p orbital, right? So there's the nucleus, there's a p orbital, one side's shaded, one side's not. This one here, of course, the whole thing's shaded. So why does putting that negative charge in a hybrid molecular orbital that has more S character, why is that stabilizing it more than ones that have less S character? What's special about, what do you see in this electron map that's not true in this one? Yeah?
Because it's a hole and the whole thing is shaded. It's not like half of it, like one side is shaded and the other one is not.
Right.
So it's like a hole.
Right, so what you're describing is the fact that there's a node here.
Yeah.
Right, so, and that node, by definition, is where there is zero probability of finding an electron. So in p orbitals, there's zero probability of finding an electron at that nucleus. What about S? It could be anywhere. It could be right next to it if it had to be. And what stabilizes negative charge? Positive charge. What is the nucleus made of? Protons, right? So when you start to think about why is this happening for the acetylide ion, the reason why is that the more S character an orbital has, the closer that negative charge can get to the nucleus, and the more stable it's going to be. Thus making that carbon-hydrogen bond easier to break. It all kind of cascades off of the idea that if I can stabilize the product, meaning that if I can stabilize this species here, that carbon-hydrogen bond is just easier to break. And we've seen this a couple different ways of why is that bond breaking versus this one. This is another example of it. Why does this work at all? Because we can actually stabilize that negative charge in an orbital that can stabilize it well enough. Okay, so the percentage S character is based on the sp hybridization, but when you go to vinylic anion, so what that's describing is if I put a negative charge onto a vinyl position, or if even worse, if I was to put a negative charge onto an sp3 hybridized, so this of course would be negative there, this would be a negative there, that these, because of the nature of the hybridization, this one here, of course, is sp2, this one here, of course, is sp3, that the percentage S character is dropping. And as a result, I can't stabilize that negative charge well enough, and so as a result, I can't create that anion easily with a base like that, as opposed to the alkyne. Okay. And I thought, again, this is a really fundamental piece of the course. Why does this happen? Why do we see this type of chemistry? It's because of where those electrons are at and how they're being stabilized. So I thought these were three beautiful pictures from McMurray, basically describing the fact that as you get more S character, what do you see in the intensity of those red regions from left to right? Is it getting more intense in an area, or is it getting spread out and the redness is going away? Maybe it's a bad picture. For me, let's take what I'm on a roll, I'll keep talking. For me, I see intensity going away, right? So from the alkyl anion, I see that charge is all localized in one area. So it's a deeper, more concentrated red, meaning the electrons are only in one part of that molecule, as opposed to when you go to the vinylic anion and the acetylide anion, you see that red charge start to spread out in the entire system. And as you guys know, though this isn't resonance, localized charges are inherently unstable. The ability to spread that charge out creates stability in whatever way. So in this case, this is talking about hybrid molecular orbitals for the reason why this is happening. If I give you resonance structures, it's resonance that's the reason why it's happening. I'm spreading that density out and creating something that's more stable. Okay. So, if I gave you a question like this and said the pKa of acetone, which has that structure, is 19.3, which one of those bases is strong enough to deprotonate acetone? So let's see, so what's the first thing we do here? Well, what's the reaction? I'm saying it's deprotonated, meaning I'm losing a proton. So I have something like this. I have CH3, C double bond O, CH3. I'm deprotonating it with a base. You can see which of the following bases is strong enough. So I'm going to put generically base there, which then creates the base, of course, would pick up a proton because it's deprotonating this and creates CH2 okay, and I know that this is acting like an acid, and they told me the pKa of this is 19.3. And over here, which one of these species am I the most worried about? Am I worried about A in this calculation or B in this calculation? A. Thanks for answering. No, it's A, right? So what am I comparing? Acidities of the acids, right? I'm comparing pKa's. So this would be the acid, this would be the conjugate base of, this would be the conjugate acid of that base, which means that the pKa's that I'm interested in are this. Okay, so as I walk down that list of examples, I have water, which has a pKa of 15.7. I have acetylide ion, which has a pKa, actually this would be protonated, so it's like this. That has a pKa of 25. I have bicarbonate, H2CO3. That would have a pKa of 64. And of course then methanol, which would be the conjugate acid of that base, which is methoxide, sodium methoxide, 15.6. I'm comparing two pKa, so on which side does that equilibrium lie? Does it lie on the side of the weakest acid or the strongest acid? Weakest, I heard that, yes, right? So if this equilibrium lies on the side of the weakest acid, then, and we're looking at these two comparisons, that acid over here has to have a value greater than 19.3 for it to work. If it doesn't, the reaction doesn't go based on the thermodynamics of the bonds that are here. So let's see, so 15.6, not strong enough. Acetylide, yeah, that's strong enough. 25 versus 19.3, it just has to be a weaker acid than this. Bicarbonate, oh, that would work great. 15.6, that wouldn't work. So this harkens back to chapter 2 in the sense of now that we're seeing these types of unique chemical reactivities, there are only certain species that will be strong enough based on thermodynamics to drive the reaction that we're even talking about. And so these are things you just want to keep in mind. And most likely for Chem 313, it's going to be a dead giveaway because you're going to see pKa's from me. So if you see that on a question, you know I'm trying to probe something along these lines. Thermodynamics. Any questions? Yeah?
So is it both B and C?
Yeah, B and C would work for me. Yeah. Just has to be a better, just has to be a weaker acid. Okay. So what was the really interesting thing? So I've shown you that acetylide or alkynes that are terminal can be deprotonated to make the acetylide anion. What can we do with it? And what we can do with it is the first carbon-carbon bond forming reaction. Actually, it might be the only one. Yeah, I think this is the only one. Do you think you should start on your information sheets? If you see carbons you need to add, this is the only way you can even do it. So let's see. So how does this go? So this would be the alkylation of acetylides. Oh. Fine. If I was to draw sort of a generic reaction mixture or a generic reaction, let's do this one. So R, C triple bond RH, it has to be terminal. Of course, the first step, you have to deprotonate it. So this is the reason why we use sodium amide in this reaction. And the reason why is that it generates ammonia. And ammonia is a gas, it blows out of the reaction, makes things relatively easy to work with. So we use sodium amide because the product we get back is this. R, C triple bond C, acetylide anion plus ammonia, and that arrow up is describing the release of a gas, so we are releasing ammonia. Now that we've created this compound can act like a nucleophile. So if I have any primary alkyl halide, so I'll describe this. So we have R, now in a second step, R, C triple bond C, acetylide anion, and if I was to put it in the presence of something that, a compound that has R, a different R, I'll put it there, and then CH2X, and X here can be Br, Cl, the usual suspects. Can't be F because F is a perfectly horrible leaving group, as you guys know, so fluorine doesn't work for this. But if I was to put this acetylide ion in with, and this is called a primary alkyl halide. Primary, right? So in other words, this had better be a carbon that has only, and I'm describing this functionality with reference to the halide. It's attached to something that only has one other carbon. That would be primary. So there's a primary alkyl halide. What you end up getting back is the alkylated product, meaning I keep my alkyne and I get back, oh, hold on. The only way you can make carbon-carbon bonds is described in that reaction there. There's other cool ways you can do it with couplings, but in this case for Chem 313, this one ends up being a juggernaut of a reaction, because basically once you do this, you've made a carbon-carbon bond, and you can be very creative with the types of compounds you use here. You can create anything with this type of reaction. So acetylide ion plus primary alkyl halide with either Br, Cl, or I. You do an alkylation reaction where you still have your alkyne, but you snap on this piece here. So, what's the mechanism? Well, that's not going to work. All right. We'll do the whole thing. All right, so we're going to leave do the deprotonation. So we have R, C triple bond CH. We come in with a strong base in this case, that's sodium plus, NH2 ... minus. I see a base, I'm using this as an acid, which means this lone pair comes in, attacks that hydrogen, breaking that carbon-hydrogen bond and putting those electrons onto that sp hybridized center. Now you can see where the ammonia comes from, meaning this becomes protonated, ammonia, plus then R, C triple bond C negative, based on formal charges. And now what happens is we have our other alkyl halide, so we're going to go with R, C, H, H. We'll just do Br. That's actually, let's make it X to be consistent with what's drawn there. So this would be X. And what occurs is a substitution reaction. So in other words, the acetylide ion attacks that carbon center. And the reason why it's attacking that carbon center is because we have this wonderful leaving group that's wanting those electrons. That's a halogen. So it gets kicked out. Actually, in this particular case, there's a very specific transition state. So this is called, we're going to talk about substitution reactions specifically two chapters from now. I'm going to introduce some terminology here that you're just going to hear again when we get there. So in this case here, if I do a reaction and push arrows like this, what I'm describing is something called a substitution reaction. So substitution. All right, I'm substituting the halogen for this. So that's what's occurring here. And as a result of that, this reaction has a very specific mechanism, which is called SN1. So this is a terminology we'll use quite a bit. The S stands for substitution. The 1 stands for unimolecular. And the minute I see this, I want you guys to amend your notes right now. This is not an SN1 mechanism, this is actually SN2. And I'll tell you why it's 2, besides me needing a tack hammer to the head, is this. So bimolecular is what the 2 stands for, and the N stands for nucleophilic. Okay, so after the dust settles, why did I know I did that wrong? It's because in this step, where the nucleophile attacks and the halogen leaves, there are two molecules, 1, 2. They're in the rate determining step of this mechanism, which is the reason why this is called an SN2, because it's bimolecular. The 2 stands for bimolecular. The other one that I mistakenly have put up there is SN1, and this is where that reaction in the rate determining step is unimolecular. We'll talk more about it next week. But this reaction here that I'm describing, I want to kind of throw this out here. This is a substitution reaction that has a very specific mechanism, which is called SN2, because there's 2 things attacking in the rate determining step. And as a result of the completion of this goes R, C triple bond C, and then this would be then C, H, H, R prime. Okay. Okay. Any questions with that? Very, very important reaction. This mechanism we're talking about, also a very, very important mechanism, but we'll talk more specifically about everything that's happening here when we get to it. Okay, so any terminal alkyne can be converted into its corresponding anion. So in this first example of 1-hexyne, if in the first step we deprotonate, and then the second step we alkylate, we can alkylate with any primary alkyl bromide we can dream of, and snap those 2 pieces together. And so in this case here, we're able to go to 5-decyne by reacting that acetylide anion of the hexyne with the appropriately spaced 4-membered 4-carbon compound, 4-carbon alkyl halide. Terminal alkynes can be prepared for the alkylation of acetylene. That's pretty obvious. So if you have any hydrogen on that carbon triple bond, it ends up being easy to remove, and thus you can use it for this alkylation reaction, which is quite important. Of course, if you start with acetylene, you could always, because you have a hydrogen there, do it again. So you could double alkylate the compound. You would deprotonate, alkylate one side, deprotonate again, alkylate the other side, which allows you to make 2 carbon-carbon bonds, and thus basically any compound you can dream of, as long as it is a primary alkyl halide. Now, why do I say that? It's because if you have a secondary alkyl halide, you end up not getting the substitution product. So let me show you what's going on there. So everything here was dealing with a primary alkyl halide because that led to a substitution product, meaning that the acetylide ion acted like a nucleophile, meaning it wanted to attack a nucleus. However, if you have a secondary alkyl halide, so in this case here, they're giving us, we won't worry about the stereochemistry of this until we get to elimination reactions in chapter 12, that if you put a secondary, and this of course would be secondary here, so this is our secondary alkyl halide center, and you expose it to an acetylide anion. Remember, acetylide anion is also a pretty good base. And that in a secondary, when you're dealing with a secondary center, instead of it doing the substitution reaction, so if this acetylide ion attacked that, let me move it over this way. If that acetylide anion attacked that carbon there, that would be the substitution product, meaning I'm replacing bromine for whatever the heck I'm adding there with that alkyne. Or this acetylide ion comes and attacks here and creates the elimination product, meaning an alkene, just like what you guys have in your notes. If you have an alkyl halide and you add a strong enough base, you get back alkenes. That if you have secondary alkyl halides with acetylide ions, you do not get the substitution product. You get only the elimination product. and not surprisingly, it takes on a mechanism that you've actually seen before, but I haven't called out. This mechanism, instead of being SN1, this ends up being, in this case, a mechanism described as E2. E stands for an elimination reaction took place, meaning you get back an alkene or alkyne. So elimination. And the 2, again, stands for bimolecular, meaning that in the rate determining step where I get my alkene, there are 2 molecules involved in that step. So let me draw the mechanism for this elimination. So this is an E2 elimination. All right, so here we go. I have my bromine here. I'm just going to simplify all the things that are on there for, I'm going after the H, there's a bromine on that carbon there. Now we have our acetylide anion. It ends up not attacking at the substitution place, but substitution spot, but it ends up attacking that hydrogen, and you've drawn this mechanism a bunch, forming a double bond, kicking out a bromine, which then would lead to hydrogen on the acetylide, and of course the corresponding cyclohexene. This is where that chemical intuition starts to come into play, meaning that as we start to have these different hydrogens and reagents with different reactivities, there are certain sites that are favorable, there are certain sites that are thermodynamically unfavorable. In this case here, this mechanism that I'm describing is this bimolecular mechanism because what's occurring? One molecule and a second molecule are involved in that elimination step, making it bimolecular, which is the reason why I'm describing it as E1 and E2. We'll get to the latter half of that when we get to carbocations for E1 and SN1. We've talked about SN2 and E2 with reference to these. Any questions? You guys have seen this elimination before. I've even used that term. I'm just bringing in this new term of when we talk about the mechanisms. Now there's certain words and terms that we are using to describe what's happening in these rate determining steps. Okay. Okay. So, prepare cis-2-butene using propyne and an alkyl halide. And when I open it up like that, you can use whatever alkyl halide you want to use. So, you want to make cis-2-butene. So my suggestion is draw cis-2-butene and see where you're going, and then work backwards to know what you had to use. It's called a retrosynthetic approach. Retro, in reverse. Okay, cis-2-butene. Let's see. So, it's an alkene. Butene, methylethylpropyl-butyl, 4 carbons. Okay, there's 2. There's 4. Did I nail it? Yeah? Okay. So I want to make cis-2-butene from propyne. So propyne, it's not giving me a 1, which means it's terminal, which means propyne would be 3 carbons and a terminal alkyne. So we're starting with CH3, C triple bond C, H. Okay, good so far? So what do I need to do first to get this to even want to react with something? I got deprotonated, right? So let's do that. So, and certainly you can use the reagents I've talked about before. So sodium amide, I'll think it's some solvent. If there's some solvent, really the most important thing is this is a base. Whatever it's in is kind of a whatever at this point. We'll talk more about solvents when we get to the mechanisms. So this plus that gives me acetylide ion. So okay, cool. And now, what alkyl halide do I need to use in order to get that to become cis-propyne? Or cis-2-butene. At the very beginning here, we just need to get enough carbons connected. We have 3, we need 4. So what should that alkyl halide look like? All right. Okay. So I see what you did. So are you hearkening back to this one?
Yeah.
Okay. So I love where you're going. We could go with this one. That would be better, right? Because we don't want to put any extra drama on the end there, because this would be. I know you didn't mean this one, but like this one here, that's a primary alkyl halide that allows me to snap a methyl right on there. So that's what I want to do. So in this case here, I would come in with methyl iodide, bromide, chloride, and I would get back this. CH3, C triple bond C, CH3. That's half the battle. How do I generate cis alkenes from alkynes? I didn't hand you back your reaction sheet, so you're kind of at a loss, maybe. Anybody have a guess? Does a regular metal catalyst give you back cis alkenes from an alkyne? I can see the wheels moving. This is a bad time to ask this, I bet. Lindlar's catalyst, poison catalyst, does that count? Okay. So the only way I can take an alkyne and get back something that's a cis alkene is if I do a hydrogenation and I use Lindlar's catalyst. Because that only gives me back cis alkenes, it doesn't give me back trans. If I asked for trans, I could have used whatever there. Yes? Maybe? Okay, I see some heads of affirmation, so I'll take that as we're doing okay. Okay. This was sort of a very rudimentary beginning to what is probably one of the major pieces of this course, and the thing that gets dragged through 314 is every reaction you learn, every mechanism you learn is associated with being able to do multi-step syntheses, meaning that you're able to take one reagent and create another. Use that reagent, use another set of reagents to create another compound, and another, and another, and another, which is the crux of pharmaceutical chemistry and basically natural product design by humans. So working in the retrosynthetic direction is what we do. We go and find compounds on a flower in the middle of the Amazon. We say, I want to make that compound. And you work backwards and backwards and backwards to a compound you can buy and then make it with that. So you're sort of learning the beginnings of this with all the reactions that you put together. And of course, this retrosynthetic path, it means you're working backwards. This last problem, we started here and said, how do I get here from there? And that's the final cherry on the top for this course, is being able to do that well. So here's an example of this. So using cis-4-octene as the only carbon source in the synthesis of butanal, use that compound as the only source and use whatever reagent you want to get to butanal. Now, that butanal structure, we don't do aldehydes till 314, so I'd have to give it to you. So I'll give you the last product. So butanal would be 1, 2, 3, 4. Butanal, if it has an al on the end, it's an aldehyde. So that's where we're going. This is where we're coming from. So let's see. So cis-octene. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 2, 5, 6, 7, 8. It's cis-octene, which means I'm going to have to screw around with this. So 1, 2, 3, 4. That's where my alkene would be. which means that on this side, that would be cis 4-octene. So 1, 2, 3, 4, 5, 6, 7, 8. It's cis because both of those groups are on the same side.
That's cis.
I might have put too much room between here and there. How would you take this compound and come up with this compound in any way? First question. Are all these carbons connected in the product? Right, so this is my reactant, that is my product. Do I have all these carbons connected the way they're connected here in the product? No, which means I gotta break it. And if I'm gonna break bonds, that would be described as a cleavage reaction. Okay, so what am I also seeing? I see I have 4 carbons. 1, 2, 3, 4. I have 4 carbons on this side too. 1, 2, 3, 4. So what set of reagents should I use to convert an alkene into an aldehyde? And if I handed back your reaction sheets again, this would go beautifully. What I'm thinking of is, well, we could do this one. Ozone plus zinc metal and acetic acid. That would work. Right, so why am I describing that would work? It's because I know that's a cleavage reaction. I get back aldehydes because I'm not using something like potassium permanganate, which oxidizes it all the whole way. So whatever functionality is there stays. So that would do it. Okay, so that's not a multi-step, but what I'm trying to draw out is the mindset. Meaning, how did I approach that problem? I knew where I was going, I knew what I had, and I sat there and asked myself, well, what do I need to do to this compound to get there? Well, I gotta break it. And hopefully that gives me the right aldehyde to work with. Okay, any questions with that? No? Okay. How about this one? I'll be a little bit quieter. You guys can probably get away with this with what you know right now. So what we just discussed will probably take you over the line on this one for the most part. So I'll give you like 5 minutes to figure it out. In your groups, just write it up behind you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's decane. And we're coming from acetylene. So you're given this, you want to go there, and you have a compound here that you could potentially alkylate twice. So think about that. Go.
John, thank you. I'm trying to participate here. So I thought, is it the reaction or learning that?
Yeah.
Okay, so it could be use a base.
I have so much faith in you, John.
Well, first I need the deprotonate in this one, so I can NH2, and then you steal one of those carbons, one of the hydrogens like that? Yeah, NH2.
Have any questions, just raise your hand. Come back and help.
Do we use NaH, NH2?
NaNH2, yeah, that's the thing.
Do we use that?
Yeah, to deprotonate first, yeah.
And do we did it twice, like once and then...
You have to do it sequentially, yeah.
Just start with that.
So that.
Yeah. And then you have H bond to C, double bond C, and then triple bond C, sorry, my bad. And then you have a negative charge and 2 electrons, and an NH3. And then
What do you get from 2 C's to 10 C's?
yeah, that's what. Well, in this example, we added 1 by doing CH3. Oh, we have to use the actual. So let's do the same one as before. So let's do CH3I, and then we get
Yeah, I probably should.
another.
Go back and see.
So we have
So at that stage there, you can tag on any alkyl halide.
So we could do as many.
You can put on as many carbons as you want to tag on to either side of that.
Okay.
Yep.
So if there's 10 total,
We need
have
8.
2. We need
You can make
8,
that
so we
alkyl
need 4
halide
on
as
each
long as
side.
you want
So we'd want,
to get the number of
4
carbons you
first
need.
because we have to do the other side. But 4 to one side and 4 to the other.
So then we're gonna use like this. Yeah, right.
No, okay. And then we have to do it again. So then we do NaNH2 to the other side, and we steal the hydrogen from the other side. So do
You can also use one super long alkyl halide and stick that alkyne at the end too. So you don't have to functionalize both sides. You could use an alkyl halide that has a lot of carbons and then stick those 2 carbons at the end. And you can rotate.
After you write, I just
Depends on what you got. Either
and then these are all CH3s. Yeah. Oh yeah, CH3.
That's only
yeah, you can totally put a heptane on there and give it to, or you'll play an octane on there. Because you're 2 carbons short. Because the assembly. That's a good idea.
And then I would take the hydrogen from the other side, and then add another 4 carbon.
Tim. What? Because this is the intermediate. We just deprotonate this or whatever it's called. And then we get this. And then we're gonna. There's a C that comes to
The carbon.
because you have to do so we have right now the baby.
So you don't want to draw it that way. You want to literally draw a 4 carbon structure at that alkyl halide that's up top there to stick all those groups, to stick that group on.
I'm gonna.
So, yeah.
We need help.
Yeah. So like what I'm saying is, instead of putting 4 CH3s, really what you want to use is
Or whatever you call it.
that, right?
Get that intermediate. That's what I got. And then you have to do this.
Like that doesn't mean this to me. This is an entirely different compound. That you're telling me there's 4 moles of methyl iodide being used, which wouldn't give you that product. Yeah. Yep. So what's up?
Okay, so I need to figure out what R you're doing.
Exactly, yeah, so you can either decide to snap it all on at once, which would mean you'd have to be 2 carbons short of decane.
So that would be heptane.
It would be, you'd want an octane here to then put 2 carbons on to get to decane and then just deal with this at the end. So you could snap it on one end and then reduce it, or you could alkylate both sides sequentially with 4 carbons and get there too. I like where you're going, right? You want to.
I got to that point. I'm pretty proud of myself for that.
So let's go with 1. So 1 on this guy like 4. first alkene in the world. But like, so you want to add on 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. That snaps, and so if you do this reaction with that and draw that product,
So that would be a lot.
be a lot of carbons, which is what you need, right? Because you're going to decade
Somehow
from
that
a
would
settling.
make that
This
triple
C
bond
plus this
into
C.
a double
Right.
bond.
And then this C goes to this C.
Or into a single bond.
Right?
Yeah, right. So that would go there, and the bromine would get kicked off. Yep. You
Not
got it.
decyl.
So
I know.
I would put the R here.
Uh-huh.
1, 2,
Hopefully that's 8 carbons.
8.
Yep.
1, 2, 3, 4, 5, 6, 7.
Yep.
And then we have
Yeah, it looks like that.
a C.
Yeah, I see what you're doing, but
Yes,
here, you don't want to, in order to do
And now we have to somehow break that triple bond into a single bond.
This is the.
how many more next to here, how many
It should be here. You could use catalytic.
So like this way too.
Wow, does that make sense?
Wait, it's an internal.
So long.
Say twice, right, and then you reduce it. Yeah.
Okay, do 2H2 and cadmium crystal. 2H2, so 2 moles of H2 and then cadmium crystal.
I feel like
Each 50 is lower.
Yeah, that would be 11.
And it's usually they do a slash.
So how do we break that?
So you know it's not carbon and it's crystal.
we do the thing that breaks there's what's the reaction that breaks carbon? I mean, there's a lot of things that break triple bond.
No, sorry. Pushing. Did I get the area push? No, you got the area push.
Oh, that's right. And then we get the decade.
All about the Sam. Here, this bump, text it. Okay. Okay. We don't have a reaction sheet, so.
I raised my hand. He's coming back over. You left your car
I don't know where the eyes go, but that's okay.
Oh, yeah. Does anybody have a picture of the reaction sheet?
I don't know. I don't know.
Oh, I'm pretty sure that has to be right. Because if that gets
I
picked
thought
up,
they would be smaller at first, but they're just.
But it's not just this.
So when you do this reaction,
yes. If there's anything break a triple bond, would you use
They show them in info.
You're just reaction. Okay. What is that? What does that go to?
Is it mine?
So we just need pure decade.
This hydrogen.
I'll find out. No, this is the.
At this hour.
It shouldn't have hydrogen. It shouldn't have any R. It should only have.
You left me before I was done.
oh, I love it.
So now we're stuck. Is that right?
Yes, it is.
Okay. Now for the next part, what do we?
Reduce that alkyne with something to get it back to an alkane. Yeah, that totally does it. Yeah.
If I'm going with smart one of the group today, this is gonna be an issue. This is going down so guys.
Yeah.
So What I used to is
Sodium ends up becoming, okay, you guys alkylated twice with the same, yeah, totally. That was
What happens to the iodine?
iodide becomes just a salt, it'll probably precipitate out with the sodium.
Okay.
Yep.
So what is the NaOH? Okay.
Okay, I think you got it there. You got it. All right, so there are two ways you can do this, right? Why is it retrosynthetic? It's because we're making so many carbons using only one type of reaction where we're stuck with that type of functionality. So we could go two ways with this. I'll draw them both up. And trust me, like in this class, I will take the ride on whatever you want to show me as long as it makes sense. I'm not going to hold you to any higher level organic chemistry thing for the reason why it wouldn't work. But if it looks reasonable, I'll take it. So in this case here, we could do it this way. We could have one would be sodium amide. And then in a second step, we come in and we alkylate it with every carbon we need. You just have to make sure it's a primary alkyl halide. So I see that I'm going to decane. I have 2 carbons here, which means I just have to make this alkane 2 carbons less because I'm going to put 2 carbons on. So 1, 2, 3, 4, 5, 6, 7, 8, and I use an iodide. So if I do this reaction, I make the acetylide ion, and then the acetylide ion reacts with this, which then gives me 1, 2, 3, 4, 5, 6, 1, 2, 4, 5, 6, 7, 8, 9, 10. Let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm trying to be mindful of the fact that this would have a linear relationship. You don't have, I mean, if you make it bent, I'm not going to hold you to it. Just know that you're wrong. So, in this case here, though, now, what do we do? Well, now we have an alkyne, we have all the carbons we need, we just need to get rid of this, so I would come in with probably 2 moles of hydrogen, because we would need both. We need to take it from an alkyne to an alkene, and then an alkene to an alkane. So hydrogenation over palladium on carbon, you could use something amazingly expensive like rhodium, I'd be fine. Just put a metal in, because you need a metal to do it. So this would then take us a decade. The other way is you could go sequentially if you wanted to make it out, if you wanted to alkylate with something a little bit smaller. So in this case here, step 1, sodium amide, but then in step 2, we're going to alkylate with something that is 4 carbons. So in this case, 1, 2, 3, 4. We'll use a bromide for this one. What does that do? It takes one of the hydrogens off and alkylates the one side. So that'd be 1, 2, 3, 4. And then this would be C triple bond C, H. And then do it again. The unfortunate thing with this reaction is it has to be sequential, meaning that you react with one side, you get your alkylated product, and then of course then you would do it again. So 1 sodium amide, 2 would be another, we'll come in with iodide with this one. Remember, this has to be a primary halogen. So we do this, we end up getting back this alkyne. 1, 2, 3, 4, C triple bond C. So 1, 2, 3, 4. There's that carbon, that's carbon. 1, 2, 3, 4. 1, 2, 3, 4. Okay. That would be 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then come in with 2 moles of hydrogen over something. Get your alkane. Yep.
If you wanted to like simplify the the steps, would you be allowed to say like 2 moles of NaNH2 and then 2 moles of your alkyl halide?
In this particular, I mean, I would take off a point for that, but the reason why I would is because you can't have the same thing at, oh wait a minute, you know what, I take it. And the reason why is that I'm adding the same alkyl halide here. If I'm making something that's not symmetric, I'd have to do it sequentially, but I totally agree. For this bottom step, you could have put this to me, and I would have been fine with it. So 2 moles of sodium amide plus, in this case, 2 moles of the propyl, or the butyl bromide. That would work for me, as long as you put the 2's in front of them. And the reason why it would work is because it's symmetric. So when it adds, I'm getting the same thing on both sides. But if I was doing something that was getting different things on both sides, I would have to do it sequentially. Yeah, that work? Yep.
So for the first one, I thought in order to do the hydrogenation with that specific mechanism or whatever, you had to have an internal alkyne. I didn't think you could do that with.
Oh, any alkyne should react with that.
It is with any?
Yeah,
Okay.
it's any alkyne. Yep. Okay. Your first foray into retrosynthesis. So ends finally chapter 9. Let's do 3 or 4 slides in chapter 10, and then I'll let you guys go on your way. It was heartbreaking to see all those crying faces from your emotions on the test. Like, I get it. You guys are trying. That was a challenging test. As we keep going, just use that test as a lesson to prepare for the next one, right? You're growing, you're learning, you're becoming, true scholars. And I know I'm pushing you, but you're also responding too. So you should feel good about that. If you're doing all that work and all that tutoring and trying so hard, imagine if you didn't do it. And I think all of us can imagine that. I can imagine it. Okay, so chapter 10. Just 3 slides, and then we'll clear it out. We'll move forward on Monday. On Thursday. So this chapter 10, we get into something we've been dealing with the whole time, organohalides. So this is something that we've been using. We're using it right here. The types of reactions that are happening is because of that halogen on there. And chapter 10 describes why that happens, which I think a lot of you have a very good intuition for why. There are a wide variety of organohalides in nature that are actually out there, actually fluorinated, iodinated compounds that exist in nature naturally, and tending to be relatively reactive because of that alkyl halide, that halogen connected to an sp3 center makes it reactive, just like it is here. So of course, the first thing we do is name it. It's an interesting group. It's something we use all the time. You're going to use it a bunch in 314. This is how we do the naming. So alkanes with halogen substitutions are called haloalkanes. The first step, find the longest chain. Oh my God, yes, right? So find the parent chain. Of course, being mindful of the fact that if you have double and triple bonds, you want to keep the numbering on those the lowest you can make them. Right, so now as we build up these different compounds, find the parent chain, make sure the alkene or alkyne is in that parent chain and has the lowest numbering it can. And then from there, it's alphabetical based on where the substituents are at. So in this case on the left, that's 5-bromo-2,4-dimethyl. The reason why the bromo is going first, the alphabet. So 5-bromo-2,4-dimethyl, I think that was relatively straightforward. I think both of those are relatively straightforward based on what you guys know. When one or more halogen is present, each are numbered and listed in alphabetical order when writing the name, meaning bromine comes before chlorine. So if you have a bromo and a chloro compound, it'd be 1 bromo, 3 chloro, 4 methyl pentane. And the last thing, step 3, if the parent chain can be properly numbered from either end by step 2, numbering begins at the end closer to the substituent that has the alphabetical preference. So you assign your parent chain, you look at what's hanging off of there, and you say, okay, I have a methyl and a bromo. It means that the side with the bromo is going to have the lowest numbering because it comes earlier in the alphabet when you have multiple things to pick from. Apart from the systematic naming convention, identification of the first alkyl group, and then the halogen provides the names of many alkyl halides, meaning that methyl iodide, so if I described it like this, methyl iodide, sometimes described as iodomethane, or chloromethane, or dichloromethane. You'll see that as solvents you probably use in organic lab. So, last thing we're going to do. What's the freaking name of that one? What's the carbon chain length?
4.
Butane. Iodos on the
First one.
on an end, which means it has to be 1.
So 1 iodobutane.
So 1 iodobutane. Goodbye. I'll see you guys on Thursday.
Can that just be the test?
I will have the exams then, so you can know.